Okay, for this example, we are given three vectors, u, v, and w, and we are told that they're linearly dependent. So the question is telling us up front, these ones are linearly dependent, which means that we can rearrange them to form a closed triangle. So we need to find the coefficients a, b, and c to make that happen, to get us that closed triangle or the zero vector. So where do we start? Right from where that equation left us off here. So we end up with our equation for linear dependence, and now we replace the values of the vectors, or each vector, with the corresponding value, and the zero vector is 0, 0. So what does that tell us? So from that, or from this, we end up with 2a minus 3b. So I'm looking at the x components here. I'm looking at our x components. So I know when I add my x components together, 2a minus 3b plus 4c, it's got to equal 0. Looking at the y components, 5a plus b plus 2c also equals 0. So for some of us, hopefully, we realize we have two equations, three unknowns. So we don't know, didn't have to come across this in grade 10. So can we solve it? Yes, we can. When this occurs, when you don't have enough equations, you take one of the variables and you set it equal to some independent variable. So let our c value equal t, where t is an element of real numbers. So it can be whatever value we want. So what that tells us is that there is going to be an infinite number of solutions here, because that c value can really be any real number. So that means our equation now becomes 2a minus 3b plus 4t equals 0, 5a plus b plus 2t. So the c value is technically solved for. Our c value is equal to t. All right. So we have one of the three unknowns, and we just do it arbitrarily, because when you have this many equations, when you only have two equations and three unknowns, we end up with that, what we call an multiple or infinite number of solutions. Yeah. All right, so we now have two equations with three unknowns. So now we go ahead and we treat it and solve it like we would with two equations, two unknowns, just with elimination. So I'm going to multiply, move sideways here. I'm going to leave that top equation alone. So 2a minus 3b plus 4t equals 0. And now remember this 4t, because I've said we've solved for t, t can be any number you want. It's just a number now. It's no longer a variable. The second equation, though, I'm going to have to multiply by 3. So 15a plus 3b plus 6t equals 0. Signs are opposite on the b's, so I'm going to end up adding the terms together. So I have 17a plus 10t equals 0. Again, the t and the 10 are, it's just a number. So we end up with an a value of negative 10/17 t. So we now have an a value, and we also have a c value. So all that's left is to do a substitution and solve for our b value. And I do recommend using the second equation, because the b is already isolated for us. So moving over here, we're going to let a equal negative 10/17 t. So 5 bracket negative 10 over 17 t plus b plus 2 times, well, t equals 0. So I end up with negative 50 over 17 t plus b, and that 2 I'm going to make into a denominator of 17. So 34, nope, try that again. 17 doubled is 38. t equals 0. So b would equal, difference between 50 and 38 is what, 12. Move it to the other side, so it'd be negative, so positive 12/17 t. So now I have all three values calculated, and we can now finish off the question by making our statement. So we know that the a value, so negative 10/17 t, multiplies our u vector, and the b value plus 12/17t multiply our v vector plus t times the w vector will equal 0 vector. And again, in the final statement here, I should add one more time that t can be any real number. So there's an infinite number of solutions here, because you can pick any number, any real number you want for t, and it will work. What this basically means is we have a triangle. Actually, we have a triangle, u, v, and w, and basically all we're doing with t is we're making it really, really small or really, really big, rotate it a little bit, okay? But the closed triangle, there's an infinite number of solutions because you can magnify it, shrink it, etc., etc. All right, and this example here, show that vector u and vector v are linearly independent, that they're linearly independent. So I'll just check on my time here. Okay, so much the same case, very, very similar to how we did it before. So for linearly independent, what I'm going to do is attempt to prove linearly dependent, just because the math's a little bit easier, because what I'm looking for is AU plus BV is equal to the 0 vector. And when I do that, I know I have two vectors, but the vectors are two-dimensional. So what's going to end up at the end of this, I'm going to have two equations, two unknowns. So it makes it a little bit easier. So I go from this. We know that we have negative 2a plus 3b equals 0. And the nice thing by doing this process, you're always proving for linear dependence, and you know if it falls apart or fails at some point, then you know what it has to be. It has to be linearly independent. So, using elimination from grade 10 one more time, let's multiply, doesn't matter, we'll multiply it by this one by 5, this one by 2, and eliminate my a term, plus 15b equals 0. On the bottom we'll have 10a minus 4b equals 0. Opposite sign, so I have to add here to get rid of the a's. So 15 take away 4 is 11b, but it's going to be equal to 0, which means b is equal to 0. So because one of our values, the b value, is equal to 0, so therefore b equal to 0, the system must be linearly independent. Vectors are not parallel or perpendicular. Okay. So one way to do it. Now a shortcut. We talked about because you know 4, and this is a alternate solution. So a whole bunch of connections, and the thing I love about this course is that there's not one way to do everything. So you look at it for a different way. So for linear dependence, vectors u and v must be parallel or collinear. Whoops, which would mean above. Perpendicular is the wrong thing to put in there. Should have been collinear. It's all right. Brain is not working nearly as fast as the hand. So, collinearity we talked about last time. Can we make it a scalar multiple of each other? Because if they're pointing in the same direction, they'll have that same direction component. So when I look at my value for my vector u, looking way up here, negative 2, 5, negative 2, 5 equals a, and up above here, 3, negative 2. Okay. What I then do is I kind of branch off for a second, and I say, okay, let's just look at the u vector for a second here. I know it's negative 2, 5. What I'm going to do is I'm going to get my x component to have a value of 1. So I'm going to take out a negative 2, which would allow me to get it to what we call, get the x component to lowest terms. Similarly, I'm going to take the v vector, and 3, negative 2, I'm going to do the same thing. I'm going to take a 3 out because I want to be able to compare x components, make them the same. And what I find is that the y components are not the same. Not the same. So therefore, they're not parallel or collinear, which means by definition, therefore, linearly independent. So kind of neat, two different approaches, gives you the same value in terms of an answer. All right, and here on the next page is the assigned homework. So once you go through the note and you try the homework and get through it, you should be able to tell me what the difference is, because that's going to be a question on the test. Tell me the difference between linear dependence, linear independence, and solve the following. So good luck, and you know where to find me if you have any questions.